Before I get started on my little rant, because today will be kind of like mostly me talking, just because I want to catch you up on a lot of stuff. I don't want us to be super behind. But before I get started on that, does anyone have any questions, comments, concerns? Yes. Yeah. Yes, I haven't sent it out yet. I will send it out today. I had a really weird day yesterday. I thought it was Sunday. Long story, but I'll send it to you today. And if I don't send it to you right after this, email me. Okay. Great question, though. And then all the recordings are posted now. I think all of them have audio. I didn't see any issues before I posted them. The names are a little bit weird, so I have to go back and rename them, but they're all there. Okay, anything else? Yes, what's up? Okay, so the exam review for Monday was a hot mess. So what I decided to do instead was the handout that I have for you guys. It was like a PowerPoint. It had a weird name on the file, but I sent it to you as like exam 2 review handout. Every slide of that handout has a link to the YouTube video where I covered that topic. So I think going through that is a lot more helpful than going through like the 2-hour mess of a recording that's like chopped up and everything. Also, I'm going to send you guys with the practice problems a link to last year's exam review because that one was a lot better. And I said I would make a video going over like extra practice problems that Dr. Roche sent out to you guys. So I will also send that. But that'll be like on YouTube. That won't like just be a link in the email. Does that make sense-ish? Okay, cool. Yeah, Monday was a mess. Technology didn't want to work. It was like only half of it got recorded. It was a hot mess. I hate technology. Okay. And also I'm really tired today, so I might not be the usual like explosive Rosemary energy, but that's fine. We're gonna deal. I am gonna zoom in a tad because it really annoys me how small this is. Okay. So chapter 15 is all about electrophilic aromatic substitution. So I'm going to write that down right here. Electrophilic aromatic substitutions, aka EAS reactions. And there's a couple pieces of that are super duper important. So I'm going to do a little star next to it. So electrophilic aromatic substitution. Aromatic, pretty straightforward. All of these reactions in chapter 15 are going to be with aromatic rings, more specifically benzene. So something people ask me a lot is like, oh, well, could this happen with another aromatic ring? It could, but for the purposes of this class, we're only focusing on benzene. So I'll do, might be. And the other really, really important part of this is substitution. So that goes in with these next couple questions on the handout. So benzene does not want to undergo addition reactions. We do not want to do additions. And the reason for that is if we do an addition reaction, we lose aromaticity. And I'll show you that in the mechanism we're about to do. So I'm not going to write like the whole thing out. But basically, it only undergoes sub-reactions. And if you break it down, a substitution reaction is an addition followed by an elimination. So don't get tripped up and be like, oh, you can't do any addition at all. You can only do an addition if it's followed by an elimination. So we take a hydrogen and we substitute it for something else. Any questions on what that means, substitution versus other stuff? Okay, so the difference between benzene and other conjugated systems is kind of what we just talked about. So benzene is a lot less reactive. So it's much more stable, which means much less reactive. And if you guys remember in chapter 13, we did those 1,2,1,4 addition reactions. Those were addition reactions. So the big difference here is that benzene will not undergo addition reactions, whereas other conjugated systems can undergo addition reactions. Those words don't even feel real anymore because I've said them so many times. So if you have any questions, let me know. All right, this is like a weirdly worded question, but that's kind of how he asks it on his exam. So what must be done in order to make an unreactive benzene ring more nucleophilic or electrophilic? All right, first of all, let's break that down. Benzene is always going to be the nucleophile. So that's part one of this question. Benzene is always the nucleophile in electrophilic aromatic substitutions. And now the next piece of that, it really, really doesn't want to react, right? Because benzene is super, super, super stable because it's aromatic. Well, there's two ways we can make it more reactive. One, we can add electron donating groups to make it more nucleophilic. Because the more electrons we have, the more nucleophilic it's going to be. And also, we're going to have a Lewis acid catalyst. So that Lewis acid catalyst is really, really, really important. It helps us do this reaction. Questions, comments, concerns? Flaggy. Okay. And then I already answered this one. I've said it like 100 times, but aromatic rings only go through substitution reactions, not addition reactions. True or false? True. Awesome. So this is true. And we already talked about it, but essentially the reasoning is it is much too stable. It does not want to lose aromaticity. That's why it only undergoes elimination. Substitution, not just addition. All right, so I'll leave this up for a second, and then we can do the reaction mechanism. And as always, I don't give myself enough room to do the whole mechanism, so I made a new page for myself. And I'm going to call this the general EAS reaction mechanism. And before you ask, he will not give you like a picture of this mechanism and make you like define the arrows or anything, but it is important that you know how to do this mechanism. So yes, you should know how to do the mechanism. And the second part that people always ask me is, I only show you one mechanism, and that's because all of these reactions have the same exact mechanism. So if you can do one of them, the same rules apply to every single one of them. So for all of these guys, we're going to start with a benzene ring. And we're going to have our reagents. So the bottom of the arrow is always going to have a Lewis acid. And the top one is going to have some reactive species. So I'm going to show you guys the halogenation. And the reagents for halogenation are Br2 and FeBr3. So specifically, this is a bromination, but we could replace the Br with any halogen, and it'll be the same reaction. Asterisk there. Iodine reacts a little bit differently, and he may have covered that in class. Basically, if we have I2, the mechanism is different, but you get the same final product, and that's all you need to know. Don't stress too much about like the differences in the mechanism. Yeah. Yep. Yeah, chlorine, fluorine, and bromine are all going to work the same, and then iodine is just a little bit weird, but you get the same product. All right. And then the FeBr3, that's a Lewis acid. And the benzene is our nucleophile. So when I say that, then people are like, okay, cool. So Br2 is your electrophile. Not exactly. So the first step in this reaction mechanism, this step you don't have to care too much about. But basically, Fe is going to react with the bromine. And in the first step, you do nothing to benzene. Benzene is going to stay exactly the way it is. All we've done is create the electrophile. And the electrophile is going to be Br, Br, Fe, Br3. And now we have a plus charge here and a minus charge here. But we really just care about the plus charge, so I'm not even going to draw that out. And this, as I said, is the electrophile. Okay, so at this point, benzene is a nucleophile, so benzene is going to attack, and every single hydrogen on the benzene ring is equivalent. So wink, wink, nudge, nudge. No, it doesn't matter, but okay, so before that, this is like a conceptual kind of thing. Wink, wink, nudge, nudge. In a benzene ring that has no substituents, all of the carbon-carbon bonds are exactly the same. They're exactly the same length. So it's not actually alternating between double and single bonds. They're all the same because it's fully delocalized. Second thing, every single one of these hydrogens is exactly equivalent. And the third thing is this is not the best representation of benzene because we have these two resonance structures where the double bonds are like flipped. Neither of these are the technically correct drawing of benzene. The best drawing of benzene would be that. I know these seem to be completely random things that I just told you, but you should know all of those fun facts. Does anyone want me to repeat any of them? Yes, okay. Just the first one. So the first one is all of these bonds are actually the same length. So even though we draw it as double, single, all of these bonds are the same, and they're all going to be between the length of a single bond and a double bond. You don't have to know what that length is, just know it's somewhere between a normal single and a normal double bond. I mean, for this exact problem, it doesn't, but I just wanted a place to slide this in so it felt natural and it wasn't just me being like, hey, know this random fact for your exam.
So, like, if you, this might be given to us, like, the circle thing for the question?
Okay. Possibly there could be a question that's a word problem that asks which of the following is not true about benzene, or which of the following is true about benzene. And that question could possibly be worded really weird. So for that reason, I am telling you things that are true about benzene, just in case that were to pop up, you know? Wink, wink, nudge, nudge. I hate this question because I got it on my final and that's what made me cry because it was like so random. But anyway, are we good with like what I mean by that? Didn't write it down. I'll tell you at the end. That's okay. No, that's why I said wink, wink, nudge, nudge, guys. Come on. But okay, so for this reaction, the reason I mentioned that is because all of these hydrogens are exactly the same. All three of these bonds are exactly the same. So we can attack using any double bond. It doesn't matter since there's nothing on it. So I like to start here just because it makes the most sense to me. And we're going to steal one of the bromines and we're going to break that bond. And bromine is kind of going to disconnect from FeBr3. And so when I draw that out, I'm going to move a tad. The other two double bonds of benzene stay exactly the same. And again, since there's nothing on the benzene ring, it doesn't matter which carbon we add our bromine to. I just do it on top because that, again, makes sense to me. So at this point, I am also going to point out that every single one of these carbons on benzene has one hydrogen on it. So I'm going to draw those out for you. Bam. Bam. The reason this is important is because now these guys are going to have a charge. This one has 4 bonds, it's happy, but this one only has 3 bonds. So what kind of charge does it have? Positive, cool. So what? Exactly. So at this point, we have an extra hydrogen here. We have a plus charge. So what we're going to do is that Br minus that we created comes back. And it's going to go over here and steal the hydrogen. Yes, and it's going to use these electrons to remake a double bond. Perfect. And so we call this an elimination, right? And we end up reforming benzene, and now it just has a bromine added to it. Oh, let me zoom out for you. Ta-da. So this is pretty much it. This is the reaction mechanism. And there's a couple like little points we need to talk about. So any questions just purely on the mechanism, how I got what I got, anything like that? All right. So what I want to say is, first of all, I'll do it in a different color. This step right here, I'll do pink to like kind of highlight which step I'm talking about. That is the rate determining step, AKA the RDS. So what that means is this is the slowest step. And that's purely like the definition of the rate determining step. The reason it's the slowest is because we went from aromatic to what? Non-aromatic. And how do we know it's non-aromatic? Because the Br made this sp3, exactly. So we went from aromatic to non-aromatic. So we can say this is a step where we lost aromaticity. We can also say this is a step where we formed the something ion. Does anyone know what this guy is called? The rhenium ion. Perfect. Okay. So let me write that in a not awkward spot. Still kind of awkward, but that's fine. So that's the step where we form the rhenium ion. And last but not least, this is the addition step. So he could use any of these like terms. He could say it's the slowest step, the step where you lost aromaticity, the step where you form the rhenium ion, the addition step. All of those things refer to this first step where we add bromine to the benzene ring. No, I'll show you the question I was talking about because I really hate that question. You had a question? Yeah.
But we know that Br is in excess.
I mean, it doesn't have to tell you that, but if it did tell you that it's in excess, that's nothing changes.
Other thing would be better, so.
I see where you're coming from, but don't think of it as like which one's in excess, which one is not, because we're just saying that this is in a solution of lots of benzene, lots of bromine, and lots of acid. Yeah, exactly. So rate determining step, that's the one where we lose aromaticity and we form the rhenium ion. And then the second step is, not super important. I just want to say that that is the elimination step. And this is the step where we reform aromaticity. And you can't see that because of this little box. Let me move it out of the way. be gone. There we go. And this is going to be the fastest step, but that's kind of obvious because this one was the slowest step. So the other step has to be, in comparison, faster. And the other big takeaway is knowing that benzene equals nucleophile. Always, we need a Lewis acid catalyst. And I'm not going to write this down because it's like a clunky sentence, but the product is simply just you add a halogen to the benzene ring. Super straightforward. Yes, so the product is always going to be you just add one halogen to your benzene ring on any position. Yeah, what's up? Yes, okay. So if you have multiple things added, that's not going to be on this exam because Dr. West said he's not putting any like multiple substituents, directing effects, anything like that. But I will tell you because this will show up on a future exam. So a weird halogenation question that doesn't follow the usual rules. Friedel-Crafts is weird, but we're talking specifically about like halogenation. So we talked about iodine. Iodine is weird. But if you see something like this, this is a super weird specific case where we're going to have multiple halogens added all at once. So we would get Br, Br, Br. Don't worry about how or why this happens because this is for the next exam. I just know this is in your practice problems, or at least I believe it's in your practice problems. So if you see it, don't freak out. This is for the next exam. But this is the only time that you're going to add multiple halogens all in one go. Well, okay, this will be in excess.
Oh.
Yeah. Also, guys, all right, so excess can also be written like this. If you see XS, that's all it means. Don't freak out. It is really lazy, and I had a friend who completely lost it during the exam because she was like, what is an extra small benzene? I was like, oh, honey. So it does happen, but I don't want any of you to freak out. All right, so at this point, let me zoom out so you can see this whole page at once. Do we have any questions, comments, or concerns? There we go. Cool, okay. I'll leave it for another second, and then we will move on to the thing that looks super complicated but is not that bad. And I think everyone looks to be good, so let's go up here. Okay, so this looks super complicated. I promise it's not as complicated as it looks. So essentially, these are the different reagents that we can have this semester in chapter 15. And we're going to go through and talk about which is which. And for myself, I prefer to write out the reagents for you guys instead of just putting a letter. So I'm going to erase these boxes right quick. Don't mind me. Ta-da. All right. So we're just going to go clockwise and we're going to talk about all these different reactions. So the first one, we added NO2 to the ring, and that is the nitration reaction. In a nitration reaction, our reagents are HNO3, and our Lewis acid is going to be H2SO4. And I will highlight that this is what we attached. Yes. Oh, yes, 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 yes. So all of these, exactly, yeah. So we can, these hydrogens on this benzene ring are what we call like, starts with an A, I don't remember what the term is, but we assume that they're there. So they're not drawn out, but you can assume that every one of these carbons has a hydrogen on it. And we're replacing that hydrogen with the NO2 or whatever it may be in each of these cases. And people sometimes ask me, like, why did you put it in a specific spot? It's just because I like the way it looks aesthetically. These could be added anywhere because we just started with a blank benzene ring. All right, so the second one that we're going to talk about is, sorry, I moved the page, there we go. The second one we're going to talk about is sulfonation. And there's a really real possibility that I spelled that wrong, but I don't care. So sulfonation is going to be SO3. And again, we're going to have H2SO4 as our Lewis acid. And does anyone have trouble seeing the yellow? Okay, cool. And the group that was added is SO3H. And while you guys are writing that down, you don't have to know what the electrophile for every one of these guys looks like, but I am just going to write it down for you just in case so you have it in your notes. So for the nitration, the electrophile looks like this. So it's just NO2 with a plus charge. Alrighty. Any questions thus far? Are we okay? All right. So, yes, okay. Next up, we have the halogenation, and I'm not going to write that sideways. I'm just going to write it to the side. And we talked about halogenation. It's just going to be X2, and the catalyst is going to be FeX3. Ow, that was so loud. And we said oh, I forgot the electrophile. That's what it was. The electrophile is going to be X, X, Fe, X3, and we're going to have a plus charge here. And then the sulfonation one it looks like that. Okay, you guys are very quiet. Any questions about what we've done so far? Yes. Yes. Yes, yes. So this H2SO4 and this H2SO4 are the Lewis acids. And then here we're going to have FeX3, and that X can be any halogen. All right, so the next ones we're going to do are the Friedel-Crafts, and these are the annoying ones. So Friedel-Crafts, something like that. Okay. If you haven't noticed by now, I literally can't spell for my life, but that's okay. So the Friedel-Crafts reactions, we have two of them. And so those are these two. And these are special because they have certain rules that the other reactions don't have to follow. And I'm actually going to switch the way I wrote this just because aesthetics. So I'm going to tell you this, You might not know what that means right now, and that's okay, but I'm going to put this here so you have it in your notes. So Friedel-Crafts reactions are special because they do not occur. Sorry, that just made me think of the Cardi B meme. So they do not occur if there is NH2 or a strong deactivator on the benzene ring. So again, this point just has to do with directing effects and multiple substitutions, which is why you don't need to think too much about it for this exam, but I do want you to have it in your notes just in case. Alrighty, and we do have two different types of Friedel-Crafts reactions. So we're going to have the alkylation and the acylation. So alkylation is when we add an alkyl group. Bam. So an alkyl group, just remember, R equals any carbon chain. And our reagents here are going to be RX. So the reason it's RX is because it's a carbon chain attached to a halogen, and that halogen just functions as a leaving group. We'll talk about that a little bit more in a second. And then I'm just going to move this slightly so it's not super in the way. Oh, maybe I'm not. Just kidding. Whatever. We'll make it work. The Lewis acid is AlCl3. Yes, so all of them are going to have a Lewis acid as the catalyst. They just have different ones. So I'm also going to write down here, Friedel-Crafts reactions always have AlCl3 as the Lewis acid. And I know you can't see it. I'm going to zoom out. So Friedel-Crafts always have AlCl3 as their Lewis acid. So if you ever see AlCl3, you know it's Friedel-Crafts. Okay, and the last one, last but not least, is the acylation. And this may or may not be something they covered either in this class or in Orgo 1, but an acyl group is another name for this carbonyl group. So if we add a carbonyl with an R group, we're going to say we attached an acyl group. Ring, ring. And the reagents for this reaction are, I'm going to zoom in to write this and I'll zoom back out, I promise. So acylation is going to be an R group attached to a carbonyl. And that carbonyl is going to have a halogen on the other side. And again, that halogen will function as a leaving group. And the acid again is AlCl3. So I will zoom out. Okay, so for these two, the electrophile is important, and let me show you why. So for the acylation, the electrophile is actually going to have two different resonance structures. Wow. So for both of the Friedel-Crafts reactions, what I want you to do is you just take the X or whatever halogen it may be off and you replace it with a plus charge. So we get R, carbonyl, replace that with a plus charge. Does anyone not see how I got that? Okay. Yeah, some people just have trouble seeing it. And then the resonance structure for this you don't have to know. Just know that the H2SO4 reacts with it and it makes it into an NO2. All right. So then the, resonance structure. Sorry, that was so professional of me. The resonance structure will look like this. Weird, right? And this has a specific name that you have to know, and it is the acylium ion. Again, there's a very real possibility I spelled that wrong. Don't correct me. Huh? Yeah. Like, I'm almost positive there's not an E in it, but okay, cool. I said don't correct me, Kareem. Jeez. Okay, I'm kidding. So yeah. Basically, you just have to know this is the acylium ion. The reason you have to know that that's the acylium ion, acylium, is because the rhenium ion sounds very similar, but it's a very, very, very different thing. So remember, rhenium is the aromatic ring, and then acylium is the acyl group. And then the other thing you have to know about this, students hate this when I say it, but I hope it will make a little bit of sense. So this resonance structure on the right, is the more stable resonance structure. The reason it's the more stable one is because the plus charge is on an oxygen, whereas here, the plus charge is on a carbon and it's allylic. Not allylic, vinylic. I'm so sorry. So if we have a plus charge directly on a double bond, that's called the vinylic position, and it's awful. We hate that position. It's super unstable. We don't like it at all. So for that reason, this is the more stable resonance structure. And that's all you really have to know. Both of these pictures are the same thing. That's the same molecule. It's the acylium ion, but this version is more stable because of where the plus charge is. Are we good? Questions? Okay. I'll leave that zoomed in for a second because I know when I zoom out, it's going to be hard to see. Oh, actually, before I do that, all right, so when you look at the acylium ion, you look at the electrophile, the reagent they give you, all you're going to do is you removed the halogen and you put a plus sign. You're just going to attach that to the benzene ring. People tend to mix up how you attach it to the benzene ring, and that's okay. But I'm telling you, the way you attach it is you just leave this carbonyl the same. You leave the oxygen in the R group, and you replace the halogen with a bond to benzene. Is anyone super confused about that? It's okay if you are, but I would rather you say it now than struggle later. Okay. In that case, I'm going to zoom out. And we're going to move on to alkylation. And now alkylation also has a special electrophile. And Dr. West actually did talk about this today a little bit. So the electrophile for an alkylation reaction, just like the acylation, we remove the halogen and we put a plus sign or plus charge. Wow, an R group with a plus. What is that? It's cation, yes, but specifically it's a carbocation. And that's really important because carbocations can do what? Rearrangements. Okay, so because the electrophile is a carbocation, Friedel-Crafts alkylation reactions have two special qualities to them. One, they can undergo rearrangements. And two, we can have polysubstitution. For polysubstitution, this is a next exam type of thing. Just know conceptually, the only one of these 5 reactions that we did that can have polysubstitution is Friedel-Crafts alkylation. And I'll repeat that one more time because wink, wink, nudge, nudge, that's a useful thing to know. So theoretically speaking, if he were to ask you a concept question, like just a wordy question with no pictures or anything, and he asked you, which electrophilic aromatic substitution can have unwanted polysubstitution? You guys would say alkylation, exactly. So that's the only one that can have polysubstitution. Yeah, so what happens is if you add the carbocation, then that carbon group can influence that to like react again and add more carbons. But we're not going to talk about why that happens until next exam. But that was a really good question. Okay. So yeah, this looks complete to me. I don't think I left anything out. So I'm going to zoom out and you guys can take a picture or a screenshot or whatever. And this is pretty much all you need to know for 15. This is like the biggest bulk of it. So how do we feel? Yes. Oh, I forget that that's new to this chapter. Okay, so yes. So what we're going to say is, let's say we have a group. It could literally be any group. I'm just going to use an R group just because, but it could be anything. So if we have something on a benzene ring, the positions right next door are called ortho. And then the next one over is called meta. What am I doing? And the one directly opposite is called para. The way I remember this, nobody else uses this, but ortho in bio, there's something called orthological species, which means they're two species that evolve next to each other. The way Katrina says it is it's on either side, so either or, either side of it. And then meta is super easy because it makes an M if you substitute it. P, you could either do perpendicular, but I am so creative. I like to say it's like the North and South Pole, so they're opposite to one another. Parallel, yeah, parallel, not perpendicular. So yeah, ta-da! That's how I think about it. What else? Okay, yes, this, and then I'm just going to say something, and I'm going to have you guys look at the questions. I don't want to spend too much time like overwhelming you in the last 2 minutes, but one thing that I really think it's useful for you to know is some of those common naming stuff. So the common names, and you know, I know there's not really any practice problems that are really good for that, but like hypothetically speaking, if you had a question that looked something like this, wink, wink, nudge, nudge. These are my special problems. You could take a screenshot or something if you'd like. Okay, anyway. So toluene looks like this. It's just a methyl. So the way we would name this is, methylbenzene. So toluene is the common name for methylbenzene. Next up is anisole. So anisole looks like this. So this is an ether with a methyl at the end of it. So how do we name this guy? Close, it's going to be methoxybenzene. And the answer is on the next page, and I don't want to like zoom out. Hold on, actually. Let's see if it'll fit. There we go. So it's methoxybenzene. Yes. It's in the 15 practice problems, but it's also in 14. Yeah. I don't know. These aren't in your practice problems, which is why you might not recognize them. Anyway, phenol. Everyone knows phenol is alcohol, but then they get this question wrong because they're like, wait, benz alcohol is not there. Hydroxy, yeah, it's going to be hydroxybenzene because that's a hydroxyl group. And then two more, and then I will set you free for the day. I know it's already 51, but that's fine. So aniline, NH2, and yes, NH2 is an amino group, hence why we have amino acids. And then last but not least, one that's important to know is xylene. And xylene, I'm going to say this and you're all going to forget it. Now, out of spite, you have to remember it. So xylene is simply dimethylbenzene, and the methyls can be any relationship to one another. So they don't have to be meta. They can also be ortho or para to one another. It's just important that you know that it's dimethylbenzene. So repeat back to me. Does xylene have to be meta to one another? No, it could be any relationship. Cool. So that is where I will leave you today. If you have any questions, I'll be here so you can come ask me. But if not, have a wonderful day. And if I don't see you before your exam on Friday, you're going to do great. I believe in you. You're going to do wonderful. Yes. Remember the crew.